Assalamualaikum and good day to everyone. My name is Noraidi Bemat Yusof, PhD student from University Technology Malaysia. In this video, I will present my paper for 2020 IEEE International Conference on Automatic Control and Intelligent System. The title for this paper is Analysis of Event-Based PI Controller and Some Proposed Improvement. Co-author for this paper is my supervisor, Associate Professor Dr. Rosby bin Mamat from Control and Mechatronic Engineering Division, School of Electrical Engineering, University Technology Malaysia. For the introduction, let me try to explain the concept of the event-based control system. Event-based controller is an alternative to the discrete controller in discrete control system. We know that in discrete control system, the sampling and the control update are looping in specific period, which known as a sampling period or sampling time. This periodically sampling and control update can be called as a time-based controller. On the other hand, in event-based controller, control updates are based on the event determined by the event detector. The question is why we need event-based controller. Either we realize or not, we are at the era of Industrial Revolution 4.0 and Internet of Things. Most of the systems now are controlled by a computer or embedded system. If we treat this kind of controller as a cyber controller, while the actuator and plants are physical, now we are dealing with a cyber physical system. However, most of the controller that we have now only focus on physical part. We don't really care and take into account how much the computational cost in our control system. For this reason, event-based controller can be a solution based on its capability to behave like the human behavior, where it's triggered based on event. This kind of triggering will give a less triggering, which means less update and eventually less computational cost. Now I will focus on the implementation of event-based PI controller. Firstly, we have a basic setup of PI controller in discrete control system. And now this is the setup for event-based PI controller, where there is an additional block for the event detector to detect the event before the controller can update the control input. In this strategy, sensor sampling and event detector is still in time-based manner. Here I will show the sequence of the event-based controller in updating the control input. First, the sensor will sample the output and the sampled output will be evaluated by the event detector. Let's say there is no event at the first sampling, so the controller will not compute any update to the actuator. Then after a certain amount of time, it's equivalent to H nominal, which is a sampling period in discrete controller. The output is sampling again, and this time the event is detected. Thus, the controller will give a new update to the actuator. A same process goes for the next sampling and it repeated periodically. In this example, the sensor is sampling 9 times while the controller only computing 6 times. This is how the event-based controller reduces the control computation. The problem now is usually event-based PI controller will introduce extra computation, and this is again their primary objective to reduce the computation. Therefore, a simple event-based PI computation is needed for event-based PI controller to be executed using a microcontroller with a low computational power. Therefore, we set the objective for this study to design the simple event-based algorithm for PI controller, and we want to test the performance of the proposed algorithm. In achieving the objectives, we set methodology as below. Firstly, we analyzed previous event-based PI algorithms. Then we did a simulation study on the high-order process model, and by using SIMC tuning rule, we tuned the PI controller gain. Next, the controller is discretized using a backward discretization. Not at the integral discretization part, there is an effect of H, which is a sampling period. After the discretization, we implement event-based saturation algorithm by the Durand and Marchand and our proposed improved event-based algorithm. In order to investigate the effectiveness of our improved algorithm, the experiment on varying sampling period and error limit are conducted for two benchmarks, which are set point change and disturbance rejection. In this slide, I will explain the comparison between original event-based algorithm by Hosen, saturation algorithm by Durand and Marchand, and our improved algorithm. The comparison are in terms of event trigger mechanism and integral discretization. Event-based has an event trigger mechanism used by the event detector to decide an event. Hausen used a delta error with a safety limit Hmax, where Hmax is a maximum time the system without the control update. For the discretization, he used a forward discretization method. In saturation algorithm, Durant and Merchant use only absolute error for their event trigger mechanism. They remove the safety limit to reduce more control update. However, they need to deal with a large overshoot to the system if the controller is not updating for a long period of time. And for that reason, they introduce the saturation to reduce the overshoot. In our proposed improved algorithm, we use the same event trigger mechanism as saturation algorithm, but for the discretization, we use a fixed H norm where it is equal to the sampling time. For the result and discussion, firstly, we like to propose a simple computational cost calculation by using a number of floating point addition operation. Let's assume addition is equal to subtraction and multiplication is equal to division. According to Horowitz, multiplication is 4 times cost of addition. And now let's take a look on the cost of saturation algorithm by Durant and Marchand as well as our improved algorithm. For the saturation algorithm, the cost is about 19 addition while our proposed improved algorithm has only 13 addition. This shows that improved algorithm has a less computation. In terms of performance, performance of event-based PI controller is measured by two performance index. Firstly, the capabilities of the method to give the same output response as a time-triggered output response. Thus, we use an integrated absolute error performance IEEP index to evaluate how much output response of event-based are different with the discrete control response. Secondly, we are looking at a computational load, which is a ratio between the control update for the event-based compared to the discrete control update. Let's go for the result of benchmark 1, which is a set point change. This is the response for the time trigger or discrete controller with 0.1 sampling time and 600 control updates. And now the green line is the response of the saturation algorithm by Durant and Marchand. We can see an overshoot for the saturation algorithm response at the first set point change because this change happened before the saturation is effective. The bottom graph shows the control update triggering where when the value is 1, the controller is updating. In this case, saturation algorithm is only updating 305 times. Now the red line is the improved algorithm response, which is able to catch up the time trigger response with only 260 updates. For the disturbance case, although saturation algorithm able to reduce the control update to 275 updates, there is an overshoot when it tries to react with the disturbance. On the contrary, the improved algorithm managed to handle the disturbance accordingly to time trigger response with only 271 control updates. The result for further investigation on the sensitivity toward sampling period and error limit is important in order to find the trade-off between the output performance and computational load reduction. For the benchmark 1, improved algorithm managed to outperform saturation algorithm performance where improved algorithm consistently produce a lowest value of IEEP with a lowest computational load. And we can find a similar trend on improved algorithm performance on disturbance rejection case, where it has the lowest IEAP and computational load for any sampling period and error limit. In conclusion, this study is set out to analyze and suggest an improvement to the saturation algorithm proposed by Durant and Marchand. The analysis comes with the two aspects, namely performance and computational analysis. Improved algorithm is proposed and compared with the Durand and merchant saturation algorithm. From the result, we get the proposed improved algorithm successfully gives a better performance with a less computational cost. Here are the references used in this paper. That's all for my presentation. I hope you can get a good information from this presentation. Thank you for listening.